All right, how is everybody doing? How is the project? Any leftover questions from the project? Except not why your program is getting seg faults. You're getting seg faults because you're doing a call on a null pointer. The question is, why do you have a null pointer? And the answer is, I don't know without looking at your code. Okay. Any other questions about the project? And so that's everything that'll be on the final. Any questions? That didn't work, did it? All right. So welcome to our last class of Computer Science 051. I hope if you look back at the beginning of the semester, you all realize you have learned a tremendous amount to be here. Haven't you? Have you learned more in any of your other classes this semester? Yay, I win. That is my goal, to be the teacher who taught you the most over the course of the semester. Whether it was useful or not remains to be seen. Hopefully it will be, okay? So today, we are going to talk about recursion. We are going to, if we have time, show you one simple trick that you will wish I had showed you a long time ago, but I didn't for a reason. And if we have time, I will also give you a preview of coming attractions for computer science in general, okay? And I should give a little time so that you can do the course evaluations on your computer at the end of the class, because I'm supposed to do that. And the evaluations help sometimes. So, okay, do you all remember this? What is this? A linked list. How many items are on this linked list? You sure? All right. What's this? How many items are on this linked list? You sure? What is this? You sure? Last time you didn't seem so sure. How many items are on this linked list? Everybody happy with that? What's coming next? A linked list of what? No items. But we know it's a linked list because it is one of these things that's self-referential, right? So we can link things onto it. So, everybody good with that? Here is what, and everybody remember now, everybody remembers now that last time we talked about the need to use a destructor to specifically delete things, right? So what we're talking about, and we wrote a destructor with a while loop, and then we wrote one with recursion and baffled everybody. So let's go back and talk about recursion, okay? Here's what we need to do. We need to get rid of all of these nodes. We want them to be gone so they don't hang around and clog up memory, right? And we already talked about how in this list here at the top, the one that starts with 10, 5, and 0, it's actually a pointer to a node that contains a data element 10 and a pointer to another linked list, right? Everybody see that? And it just so happens that down here is a linked list. Well, it also so happens that this is a state we can pass through to get to the end of deleting all the nodes, right? Is this second list right here not the first list with the first node deleted? It is, right? Is not this list here with 0 the same as the list above with the first node deleted? It is, right? Is this list down here with nothing on it not the same as the list above with the first node deleted? It is. Everybody's with me on that, right? Hands up if you agree. Good. Okay. So the question is, how do we go about transitioning from this state right here to this state down there? How do we get from the first list where we have 3 items to the second list where we only have 2 items? What do we have to do? I'm just sure we can create a temp. Where do you want to create a temp? We're going to be creating lots of temps when you're dealing with pointer, so it's almost never the wrong answer. Almost. Okay. Okay, so we have not conversed about this before class, right? So I did not prep you with that answer. Because what you're saying is create a temp node right here, pointing at the next thing. And so we're saying if head is not null, because we need to worry about the case where we have an empty list, If head is not null, temp equals head get next node. So temp is pointing at that node, right? Is that what you were trying to tell me to do? Yes, okay. All right, so we have temp pointing there. Now what do we have to do? Delete head. If we delete head now, head will be gone, and we'll be left with a list where temp points at 5 and 5 points at 0. So if we just do this, that's weird. I wonder where my picture went. Uh-oh. Sorry, 1 second. I made a mistake in drafting my picture, which is not uncommon. So what we can do is after we do this delete, if we think about it, temp is pointing to 5, is pointing to 0, is really the same as this thing down here, right? Is it not? Right? So if we say head is not null, temp gets pointing at this thing, delete head, it's almost as if temp is now the head of that list. Isn't that exactly the same that happened? Only thing that's changing is, in this case, we have this thing called temp. In this case, we have it called head. But it's just a name. The pointers are all the same. Yes, sir, Kevin? Nope. We're pretty much purposely losing this box. Did you say temp or 10? Yes, we are deleting 10 on purpose. We're trying to get rid of it. So it's gone. Yeah, Jules? Delete works just like new. It works on pointers, except whereas new calls something new into being, delete destroys it. And I'm sure there's some existential question there better left for the philosophy department. Okay? But it's gone as far as we're concerned. Okay. Everybody with me on this? Yes? All right. So we've deleted the first node. Now what are we going to do over here? Create a temp, because why? That's our algorithm. So let's create a temp. There's temp. Well, I'm just telling you the algorithm when we're using names a little bit. Okay, we're going to change it up, and I'll show you how it sort of works in a minute. Okay. All right. So now we have a temp. It's pointing at this. Is that where you want it to point at? The thing that the head points at a node that points at something. That's what we point temp to. Then what do? We delete head. Delete head. And after we delete head, what happens? It's almost as if temp is the head of this list down here, right? Because we have a pointer. It is. It's exactly the same thing. It's just the naming is a little bit confusing, right? Yeah. If we deleted head, if I'll delete head, literally what happens, and I'll just show you, is all this goes away. And if we have a pointer named head, it's a dangling pointer. But now we still have this list, except the head of this list is temp. Temp and head are really the same. Right? So, everybody with me? Yes? No? Hands up if you're with me. Hands up if you're against me. Just checking. Okay. All right, so we get down here. What happens? Create a temp. What is temp going to be? Temp is going to be what head, the head points at something and we grab the pointer out of there. So in this case, temp becomes null, right? And we execute this code. Is head not equal to null? Create temp, and then we do what? Delete head. When we delete head, it's like temp is now the head of this null list. Yep. Okay. We haven't even talked about how we're changing these pointers. I'm just showing you the algorithm. Okay? I'm just telling you conceptually what's going on. Just don't worry about that yet. Okay? Head is not advancing. I'm just telling you conceptually, if we delete this and we have a temp, it's just as if temp was the head of the next list. It's just a naming thing. Head as a It's confusing because I'm using the terminology and I'm trying to stick with what I used last time. It was confusing, which might have made a mistake. I'm going to change it up in just a minute. But head just is a generic reference to the first pointer that points to the rest of the list, rather than a very specific memory box. Okay? Yes? It's one of them. Yep, one of them. There's many ways to do things, right? Like many, many, many ways. But I'm showing you this one. This one's also going to be recursive. It's just slightly different than the one we used last time. And we'll look at both of them, okay? All right, so finally we get down here to the end where we just have this left. And do we need to create a temp? Why not? Because the list is empty. Head is null. The list is empty. We have deleted all the nodes. Great success. We're happy. We can go on with our day. Okay? Sort of. All right. Everybody understand what we're doing? We're deleting the first node. We're getting a link to the rest of the list, a link to the list that's pointed to by the first node, and then we're deleting the first node. So we get a link to the rest of the list, which looks like this. Then we delete the first node. We get a link to the rest of the list. Then we delete the first node. We get a link to the rest of the list. There's no first node to delete, so we're done. Thumbs up, thumbs down. Yes, you in the back? Anybody? Any questions on this conceptually, right? So here's our algorithm. Delete the first thing on the list, and then delete the other list that's sticking out from the side. Delete the first thing on the list, then delete the rest of the list that's sticking out on the side. Yes? You're all very quiet again. I don't know why. Either I'm just being... Pardon? You can't delete all the things at once, because a computer is what? But it's stupid. So you can only do one thing at a time. So we have to do step by step. Yep. No. We haven't talked about any while loops, have we? We've just talked about how. Okay. So let's actually look, since we're getting to the point where we have questions about this, let's look at the algorithm for this. Okay. You all ready? Pardon? Yeah, we'll write some code. Do you want some code? You all ready for code? There's your code. Blow it up a little bit. Okay. And let me just make some of this other stuff disappear. Okay. So here's our code. All right? We're going to write a function called delete recurse. And delete recurse doesn't have proper spacing. Looks better. Okay? Delete recurse. And what it's going to say is that here is a link to the front of the list. It's a pointer to the frontmost node on the list. All right? So this is the head of the list. Why are you shaking your head? Yes, you're calling the function inside the function. Why not, right? We have a function that's going to delete stuff. It works on a linked list. So why not call it on the linked list that's inside the first node? So here's what we're going to do. We're going to say we're going to create a temp node. We're going to make it null initially. We're going to say if this head pointer is not pointing at null, which means there's something to be deleted, then what we're going to do is we're going to keep a temp node, which is the link to the rest of the list, just like we were doing in the example, right? We're going to delete the front node, so it's gone. The first node's gone. And then you know what we're going to do? We are going to delete the rest of the list by calling what function? The same function. Does it seem bizarre to you that you can call the same function from the same function? How many of y'all think that seems bizarre? If you were not raising your hands, you are either confused or a genius, like one end or other of the scale. Because when you first see this, it is the most insane thing you could possibly imagine, right? You have a function and you're calling a function inside a function. What the heck? Yes? Well, let's talk about that. Like at some point we get down here and it's null, how do you escape? We're going to talk about that. But for the moment, it's baffling and weird that a function can call itself, right? Everybody agree on that? It's baffling and strange because you don't quite understand what's happening yet. Every time you call a function, the computer, the compiler, the thing that's running, makes a little space for that function to run. It makes some space in memory. It puts the parameters and things that you have passed into it, and it gives it some space to work. Okay? If you call the same function from the same function, it gives it a copy, and it makes a different space for that next copy of the function. If you call it again, it makes more space for the next copy of the function. The computer is stupid. It's stupid fast. It is not limited to one copy of any particular function. Every time you want to create a new one, it goes, I'm dumb. I will just create a new function. It doesn't understand the name. It doesn't understand the fact that it's the same thing being called. All it does is what it's told. And it doesn't look to see if it already has one of those functions existing. It just creates a new one. Everybody with me on that? So when a function gets called, there's a little bit of space reserved for it. And if it gets called again, it reserves some more space. And if it gets called again, it reserves some more space. Okay? Yes? So just because you think of a function as a name and only exists once, it can actually exist many, many different times inside the computer. Okay? What's the point of deleting the memory? Because otherwise the system will get clogged up over time. That's a separate topic that we'll talk about later. Okay? So the question is, doesn't recursion use memory in itself? Yes, but a different type of memory that's more easily reclaimed is the answer. Okay. All right, who's with me still? So let's draw a picture of how this works. Might that help? So here's what happens. We have, let's say we give it the link, we call it once, and we give it a link to a bunch of nodes. So here is the first instance of our variable, our function named delete recurse. By the way, can you have multiple variables that have the same name? Can you? If they have what? Different scopes. So, right? Because when we had our programs, we had multiple functions that maybe had a variable named temp in them. We might have had multiple loops that had something called I, like a for I loop, right? We can have multiple variables have the same name, and we can tell them apart because of their scope. Yes? We can have function calls that have the same name, and we also tell them apart based on where they are called. They each get their own little bit of space, sort of like they have their own scope. Okay? Everybody with me on that? So, we call delete recurse the first time, and what happens? What happens in our algorithm here? Let's step through and see. We're given a pointer to a front node. There it is. Is this node null? It is not, because there's something there. So we say node temp equals null. We create a temporary pointer. If front does not equal null, which is what we're looking at, and we say no, that's not null, what happens to temp? Temp is essentially the same as this one right here, right? Yeah, the arrow that points from inside 10 to 5, where I'm trying to make my cursor. Sometimes my cursor gets really big, and you can see. There, right there, right? Does that make sense? So temp is going to be the same as that. We're not going to draw temp. What happens then? We delete the front node, and then what do? We call delete recurse with temp. So now we have a second copy of delete recurse. But because temp was this thing, now delete recurse points at that. Pardon? Yes, it's a copy of the address, right? Remember, because we're dealing with pointers, we're drawing them this way, but they're really just boxes that have a memory address. So the memory address of this pointer from 10 to 5 gets passed into this. They have their own separate These are actually called stack frames. Like every time you call a function, you get a separate frame and you get a separate stack frame for each. You don't really know that, but just technically that's what they are. Okay? So the first delete recurse got called on this list. The second delete recurse got called on the list with 5 and 0. Shall we step through the code and see what happens with this? Why don't we? So what do? We create a temp. If front is not equal to null, here's your front pointer. Is it equal to null? It is not. So we create a temp pointer, which is front get next node, which is the same as this one right there. And then what do? We delete the first one and then call delete recurse again. So now we get another stack frame that now points at that list. Everybody with me? Yes? Yep. Just because that's how it works. You probably could. Why isn't delete recurse inside the if statement? It could be, but this is fine. Okay. It works. It'll end up working exactly the same way. How's that? All right. So we have our first delete recurse, which points at that list. We deleted something. We called delete recurse again. It points at the second list. We deleted the first node. We called delete recurse again. What happens? We do it again. So now we get one more stack frame. Like this. And this one points at nothing. Okay? This one points at nothing. Everybody with me? So let's look at our code. If front is not equal to null, is front equal to null? It is. So we don't do this stuff in here. Oh, wait a minute. You're absolutely right. That should have been inside the if statement. I see now. I see the errors of my way. The error of my ways. There we go. Sorry. Because otherwise, we will never, ever return. Sorry about that. Thank you. If I had candy, I would throw it to you, but we ate it all. Yep. You will automatically return even if you don't write return. Functions always return. Yep. It causes students to be confused because that's the way we did it last class, and everybody looked at me like I had hit you with a bat or something. So I thought maybe this way would be easier to understand. Okay? All right. So everybody with me on this so far? Right? Each time we call delete recurse, we get to the bottom. So here's what's happened. In this first delete recurse, we executed if front equals null, temp, delete front, and we called delete recurse, right? Have we ever executed the return statement yet? We have not. So what happened was this. We made one call that went to this delete recurse. This delete recurse stepped through the code. It did this stuff. It called delete recurse. Has it had an opportunity to return yet? Everybody with me on that? It has not. So what we'd have is we have this. Like we had one thing here, one call here. What happens next? Another call down. So we've called and called and called. But have any of these functions or methods yet executed their returns? Everybody see what I'm saying? Like each one, we executed the if front equals not null, temp equals front get next, delete front, delete recurse. But we haven't executed the return. They just haven't done that yet. All right? Sarah, you good? Okay. All right. So what happens? When it's null, it says if front does not equal null, what do? We skip all this stuff, and then what do? Return. So the thing that happens is we return, and we don't return back to the beginning. We return back to where the function was called from. So this function returns to this function. And when it returns, where is it actually returning to in terms of the code? Like what line of code was it executing? It had just executed the delete recurse. So what executes next? Return. So what happens is return returns. Yep. Mm-hmm. Nope, because it's already done that. Because every function does all this stuff before it calls delete recurse. When this function finishes, the only thing left to do is return. It doesn't start over again. It picks up where it left off. If you think about like when you call a function, like if you do double y equals power 2 comma 2, right? When that function returns, it just goes back to where it was called from and keeps executing. So the power function, it goes off and does the power function, it comes back, and then it keeps on going. The same thing in this case. So what happens is after delete recurse is done, it comes back and it picks up where it left off, which is return, and eventually what you see is this. You have one function points at a list, it calls the next that points at a list, it calls the next that points at a list. Once we get to the end where everything is null, then, and only then, does this one returns to the past one, which has nothing left to do except return itself, which has nothing left to do but returns itself, and so it gets back to where it came from. Okay? All right, this in a nutshell is recursion. Recursion is when a function calls itself. And a recursive function has to have, all right, everybody see this, right? A recursive function has to have something very important. And the very important thing that a recursive function has to have is a base case. The base case in this one is if front is null. Because you have to be able to know when to stop recursing. In this particular one, we stop recursing when front is equal to null. All right? Everybody sort of on board with this? Yep. So front is a parameter that's passed in. So it gets created temporarily for each one of these stack frames. So no, in a sense it doesn't. I mean, we'll see if it's there or not. We're going to run this code and look at it and we'll see what happens. But each time it's being passed in, it's just a parameter. The parameter is included as one of the local variables inside the stack frame, and then it disappears and goes away. Yep. Mm-hmm. It's not working like a while loop. A while loop is what's known as iteration, where you do one thing after the other. Recursion is very different than iteration. So it works because... Yeah, it's normal. Yeah, it's normal to they accomplish the same thing, but in very different ways. Iteration says, do this one, then do that one, then do that one, then do that one. Recursion says, do this one, and then do the same thing to the rest of them. Recursion says, now I have a smaller set, do it to the first one, now do the same thing to the rest of them. And so it functions as almost like iteration, because you're doing the first one, and then when you do the same thing to the rest of them, you're doing it on the first one, so the order is the same. Okay? Yeah. Okay. What is a computer program? It's what? Oh, come on. What's a computer program? I'm going to run into you at your 25th reunion, if I'm still alive, and I'm going to ask you, what is an algorithm? Like there are a few things you need to take away from this class. You have to understand what an algorithm is. What's an algorithm? Very good. That's going to be on the final now, because only half of you got it. An ordered series of steps used to accomplish a task. What is a program? An algorithm expressed in a way that a computer can execute it and a person can understand it, okay? So we have different ways of accomplishing the same thing. We can do something iteratively, or we can do it recursively. Does the computer care? Who cares? So recursion is a very powerful mental concept, because what I'm giving you here is literally like the simplest example of recursion you possibly can do. But later, you will learn, if you keep going in computer science, that there are algorithms that you can do recursively in like a few lines of code that are tiny, that are incredibly complex to be done iteratively, and on occasion the other way around. So it's a tool about how to think about solving a problem. Okay? There are actually entire computer languages that essentially do not have iteration. Like they just don't have a for loop. What do they have instead? Recursion. And let me tell you, they're great languages. Like Lisp is one of them. It's an artificial intelligence language. They do have loops. You can do iteration in it, but it is designed to solve all your problems recursively. And when you actually think recursively, great things happen. Okay? So does that answer your why? Okay. All right, so everybody kind of see recursion here. Yes? Do you think on the exam, given a recursion problem with a linked list, you will be able to draw what happens with it? Do you think that would be a good thing to practice? I think so too. All right, take a 1 minute break in place. Oh wait, and then we're going to run this and I'll show you one more thing. So stand up, come on, stretch. All right, welcome back. Welcome back. Sorry, is that a little too much? Can you all still hear me in the back? I messed with the volume. Okay. All right, so here's what we're going to do. We have actually some code we've been working with our recursive deletes. How about we just type this code in, we'll actually just literally copy and paste it because we've already developed it, and we'll see what it does. Does that sound like a good idea? So here we are. We're in our recursive delete program. We already wrote something last time in the linked list, which we called delete list recursive. We're going to call this one recursive delete, and we will compare the two to see what the difference is, okay? Okay, so here we are. Oh, and then we want to put this in the destructor. So let me just make sure everybody's on board with what I just did. I took the code that I showed you called recursive delete, and I added it to the trial class. Okay? The trial class. Wait, I was looking, sorry, linked list class. I've been spending too much time looking at your Project 5 stuff. Okay, so I added it to the linked list class. Okay? This one is called delete recursive. We'll see the difference in just a minute. Okay? Because we did one last class, and we'll do one this class. Okay? So we did this algorithm we just explained, delete recursive, and I added it to the destructor so that when the linked list is destroyed, we will see what happens. Okay? Remember, in this, we have a destructor in our node class that prints things out. So we're able to see when the nodes are created and see when they are destroyed, right? Do you normally have to print out when things are created or destroyed in the constructors or destructors? That is for what? Educational purposes only. Okay, so let's just make sure this compiles. Uh-oh. Delete recurse. Oh, that would be recursive, right? Did I screw that up? Where did I screw up? Oh, that would be why. Okay. And I, of course, didn't change that over there. All right, well, apparently I just changed the name randomly between our example and now. I apologize for that. So let's just make it. Thank you. All right. Human compilers, is this going to check? Is this going to be fine or not? All right. So now we can run this, and what are we going to see happen? We should see that we add an element 23 to the list, an element 14 to the list, an element 9 to the list. And then, because we have these curly brackets, the linked list object will go out of scope. When it goes out of scope, the destructor gets called, and it will call that method that we just wrote, recursive delete. And what will happen? In what order? All right, so we should see 9 disappear first, because remember, we're adding to the front of the list, not the head. So after this, the list order is going to be 9, 14, 23. When we delete them, we should see them delete in order, 9, 14, 23. Okay? Everybody on board with that? Let's actually see if that's the case. Oh, man. Wait a second. Hey, look over there. Well, I fixed my problem. That worked better when I teach on the chalkboard. Sometimes I would make a mistake on the chalkboard, and when someone said they made a mistake, I would literally go, oh my God, and everybody in the class would turn around, and then I would just erase it, and they would go back, and I would be like, God, I can't really do that on video. So let's see what's going on. Is our add element adding to the front instead of the back? No. Are we calling the right? Oh, it's because I called delete list. We wrote a delete list thing that does stuff. Recursive delete head. Did I get the order wrong? Hang on, I'm just going to put out put a little thing in here. By the way, this is what I spent a lot of yesterday doing, because you all were emailing me with, why doesn't my code work? So. Aha. So interestingly enough, our recursive delete is not being called. Why isn't it being called? Wow, this is going really badly wrong, and I can't understand why. Any ideas? Anybody see anything in the code that would do this? Well, what's interesting is that when we run this, we're not even seeing, we're seeing linked list being destroyed, right? Where is that? So it's being destroyed, but it's calling recursive delete head. All right, let's put a little comment in here. Maybe we had the I'm just confused why it's not deleting in the order I expect it to delete. So. Well. Whoa. Accidentally deleted that somehow. That would probably make things better. Okay. Wow. I have the wrong file name. See that? I accidentally have a C at the end. So every time we're compiling it, I'm actually running the old version that we didn't make any changes to. I apologize for wasting your time so much. So Anyway, how about we actually do this correctly? There we go. All right. Sorry about that. Now do you believe that it's not just you who has little problems that have to be fixed all the time? No? We're all human, we make mistakes. So, all right, now we run this, and now we see them being destroyed in the right order, 9, 14, and 23. Okay? Did we use a while loop to do this? We did not. All right, but remember just like 5 seconds ago they were being destroyed in the other order? Why was that? So let's look at the difference, okay? All right, so here is our recursive delete, which we did today, right? And then over here is what we called something else. Delete list recursive, okay? All right, so here is one, delete list recursive, and we said if it's null, just return. Otherwise, delete the rest of the list, and then delete the head node. In this one, we said if it's not null, delete the front node, and then delete the rest of the list. Both were recursive. Both delete the list. It's just this one says over here, first delete the rest of the list, and then delete head. Where this one says delete head, and then delete the rest of the list. Right? They are doing the same thing. They are both calling the next function down. It's just one of them deletes, the one that we just worked on, deletes the head of the list first, and then deletes the rest of the list. While the one we wrote last time deletes the rest of the list, and then after that returns, deletes the head node. Who's with me? Who cares? There's a difference. One is called head recursion and one is called tail recursion. Okay? Head recursion is where you do things first and then call. Tail recursion is where you recurse first and then do things when you come back. It's not going to make any difference for this class. All right. Do you think you could draw pictures of both of these? Do you think it would be a good idea to practice? Any questions on recursion? Every function returns, because when you call a function, every function that you need to know about returns. Okay? Except, I'm not even going to get into it, except every function you need to know about returns. It always returns to where it was called from, like the same line of code. It goes back to where it was called from last time. Not the first one. If you have like a recursion down and down and down and down, it doesn't suddenly go back to the first one. It goes through all the steps in between as well. I will give you some practice recursion problems that you can run in the exam or before the exam. Okay? All right, that is the second to last full topic of the semester. Any questions on it? Going once. Yes, sir. The one on the right deletes the last one on the list first. So it deletes, if the linked list, if we draw it going from left to right, the one on the right deletes right to left, and the one on the left deletes left to right. So the right one is the one we just did today. And so this one? Oh, this is the one we did last time. It differs only in that instead of deleting the head node and then doing the rest of the list, you do the rest of the list, and then when it comes back, deletes the head node. The difference, there's only really two differences in that. Notice this one says delete list recursive first, and then delete head. Do you see those two call? This is the recursive call because it's calling itself. This one says delete first and then do the recursive call. We just switch the order of the two lines. But it changes the order in which the nodes get deleted. All right, last question, 17-second rules in effect. Go ahead, go. Yes. Because what happens this is it says, okay, delete this list, and this list is the one that's in the head node. So it goes off and it does that deletion. And once it deletes that, it comes back and then deletes the remaining node. I sort of know. I actually drew over it. Sorry. I can't. I would otherwise. So just pick whichever one you're comfortable with. So. You'll get more exposure to recursion. This is really your basic introduction to it. So. Any last questions on recursion? Okay, I want to show you one thing. And we'll just do it quickly here because it may be useful to you. Okay, what is this? What does that do right there? Creates a pointer that points at a new node. Okay. What does this thing right here mean? It is the address of a node. Okay. What does this thing right here, when you say new node 7, what is that going to be? But what is this function new going to return? The address of a new node. Do you have to look at this right here to know that this over here is going to return the address of a new node? You don't, right? Because you know new node automatically returns a pointer to a new node, correct? Computers are dumb, but they're stupid really fast. One of the things computers can do is figure out what the return types of things are going to be. So when you are coding, you can also, instead of just using this node star, you can also use the keyword auto. And what auto tells is the compiler to figure out what the hell kind of thing this some other node is going to be, and then make it that. In this case, auto is going to be a node star. The compiler is going to go, okay, I have to figure out what type some other node is. And I know when I look at new node, it's going to be a pointer to something. So auto will figure out that it's a pointer to a node. Auto can figure out other things as well. Okay? So auto makes your life a lot easier. Yes? I don't know if we've included the string class here, so it probably wouldn't work, but I think if you have included it, it would know that this is a string. If we try to compile it, it probably wouldn't work right here because we haven't included the string class. Yep. Because it looks at it and it goes, hey, I know 12 is an int. I know something with this is a decimal. I know a thing around double quotes is a string. So auto will figure that out for you. Yep. I don't know. Yep. I don't know. You'd have to experiment and see. So if we did auto, like result equals int divided by double, it would probably figure out it was a double, I would suspect. So it's not entirely stupid. So if you can understand the rule for it, the compiler can too. All right. How many of you wish you'd known this earlier in the semester? Why did I not tell this to you earlier in the semester? Because you need to understand that when you're dealing with variables, you have to know what type they are. Now that you've been through the semester and you're going to understand what the type is, it's safe for you to use auto. Okay? Yep. It'll look at it and assume it's an int, I'm pretty sure. There's another tool that will tell you what auto thinks it is. I don't remember what that is off the top of my head. Yep. So here's the problem, is that in some situations, you have to like keep careful track of what the type actually is. That's why I don't teach you auto at first, so that you learn to keep track of what the type is. Now later, if you're using auto and it's not working the way you expect, it might be because auto has given you the wrong type. Okay. So go forth and do things automatically. Yes? I don't, personally. And the reason I don't use auto is because when I learned initially C and then C++ later, auto was not part of the language. They added it later, and I'm just not in the habit of using it. The time I would use it, though, is if I were programming in C++, and some of these things like node is a pretty small name, a class name, but sometimes you get class names that are things like, you know, window drop bar with shadow that's 12 pixels wide, and the variable name is like this long. And instead of typing that over and over and over again, which how many of you have programmed in Java? Most verbose language ever, right? Because you have to type all this stuff over and over again. You can just use auto, and you don't have to type these huge variable names. It's mostly a convenience for the programmer, but it can also get you into trouble if auto comes up with something that you're not expecting. Okay. So that is my parting hint to you. Professor Maloof will probably yell at you for using it or something like that, but I wanted to make your lives a little bit easier. Any last questions about the course? I will send out the list of exam topics tomorrow. I'll have office hours next week. I'll be around if you need to talk to me. I will provide some tips and sample problems and stuff like that. All right, I would like to, just for fun, I'm going to stop the recording. Goodbye. Thanks for watching the videos.